All right. Now, what's nice about these triangles is they form a consistent ratio. Their three sides form a consistent ratio that stays true no matter how big or how small the triangle is drawn, as long as they have these three angle measures for the interior ones within their triangle: 30-degree angle, 60-degree angle, and a 90-degree angle. All right. So in a 30, 60, 90 triangle, the sides across from the 30-degree angle is always the shortest side. And we've talked about this. We know that the smallest angle corresponds to the shortest side. The 60-degree angle, which would be the middle one, corresponds to the longer of those two legs. And then the hypotenuse is always directly across from the 90-degree angle. And hypotenuse always being the longest side. All right. Now, talking about where we're going to get this from, right, where these ratios come from, let's think about a 30, 60, 90 triangle here. If we were to, let's say, reflect that, we'd end up with an equilateral triangle. Three 60-degree angles, one here, and then the two 30 together will make it another 60-degree angle. We know equilateral triangles all have the same length. Each side would have the same length. Okay? Well, because we know that they have the same length, right, we know that we can actually look and find a couple of those ratios that we're talking about. Okay? We know that this side down here is going to be half the length of the hypotenuse. Okay? Because if it's an equilateral triangle, these are all the same. Well, this side down here is always going to be half the length of what the hypotenuse is. We're just looking at this triangle on the right. Now, we could also figure out what this length is going to be here using the Pythagorean theorem, right? Because we know that if we made this length S, let's say A, the length L was B, and length H was C, A squared plus B squared equals C squared, we could solve for B to get what our B length would be. And what we end up getting, if we use the values of L, S, and H, but what you end up getting is L equals S radical 3. Okay? Now we're going to use a couple different variables here when we talk about this, but the ratio that we're going to be finding, a lot of times we use A, it's going to be A radical 3 would be this length. This one down here would be A, and the hypotenuse would be 2A. Okay. Now, the reason why we use a variable instead of an actual number is because we don't know what these lengths are. But we do know that these lengths represent, that these variables A represent the ratio that is consistent no matter what within this white 30, 60, 90 triangle. So A, 2A, A radical 3. I'm going to show you how we're going to use this setup of ratios to solve for missing lengths. The nice thing is we know if we only know one of the side lengths of this 30, 60, 90 triangle, we can find the other two. Okay? Whereas with the Pythagorean theorem, you would need to have two sides to find the third one. In special right triangles, you only need one. All right. Here's a first example. It says A equals 5. So this short length right here, it equals 5. We want to figure out what this length and this length are. Now, the first thing you would do to set it up is you look at what this length is and what that represents. We know it equals A. Okay, A equals 5. To find, once you know what A equals, you can plug A into the other two to get your other two lengths. So up here, I can plug 5 in, and I get 5 radical 3 or that length, for the hypotenuse, well, that's 2 times 5, which equals 10. That's the hypotenuse length. Right? It's pretty straightforward when you're given the shortest length in the 30, 60, 90 because that equals A. Okay? We know that that's going to be kind of the base equivalent of what you're going to need to plug into your other 2 side lengths. Gets a little bit harder when the lengths they give you are either the longer leg or the hypotenuse, or when they start giving you lengths that are radicals. It's a little harder in those cases. Okay? But in this one, we'll get 5 radical 3 for our longer leg and 10 for our hypotenuse. Okay, 5 radical 3 and 10. All right, here's one where the length we're given is the length of the longer leg. And we know it's the longer leg because it's across from 60. Right? So this is the equation I need to focus on to start. A radical 3 equals 7. Now, what I need to do, I need to solve, okay? I need to solve for A. So, let's see, A radical 3 equals 7. So to solve for A, I've got to divide both sides by a radical 3. This will cancel out. I get A equals 7 radical 3. Excuse me. All right. This is something that we need to address. Do you guys remember? What do we have to do when we have a radical in the bottom of a fraction? You guys remember what that's called? And this is something that you may not have done this before. Okay. We don't like having radicals in denominators. Okay? So we want that radical to be in a numerator. So what we're going to do is something called rationalizing our denominator. Right? So to change, we're just going to get an equivalent fraction, but we're going to get an equivalent fraction with the radical on top. The way we do that is you multiply the top and bottom of the fraction by the radical that's in the denominator. Okay. So again, I know it'll be equivalent because I'm multiplying the top and the bottom of the fraction by the same thing. So I multiply straight across, I get 7 radical 3. Radical 3 times radical 3 is 3. Okay. So that's called rationalizing your denominator. You got to multiply by the radical that's in the denominator. So we get A equals 7 radical 3 over 3. This is the value we have to plug in to get our lengths for our shorter leg and our hypotenuse. So the shorter leg is pretty straightforward. It's just equal to 7 radical 3 over 3. The hypotenuse, a little more difficult. We got 2 times 7 radical 3 over 3. Now, if I write this as a fraction, 2 over 1 times that, just multiply straight across. 2 times 7 is 14. Radical 3, 1 times 3 is 3. So our hypotenuse is going to equal 14 radical 3 over 3. If you're multiplying a number times, like we have up here, 2 times 7 radical 3, you can only multiply the number times the number, right? So you can multiply numbers times numbers, and you can multiply radicals times radicals, but you can't multiply a number times a radical, which is why they end up being separate from each other. All right, I think we only have a couple more examples. So again, these were our solutions. We got our 7 is what we were given. 7 radical 3 over 3 was equal to the shorter length, and the hypotenuse was 14 radical 3 over 3. All right, here's one where we get we're given a hypotenuse. Okay, our hypotenuse length equals 1. So this is the equation we're going to focus on. 2a equals 1. I need to solve for a. So I divide both sides by 2. I get a equals 1/2. I recommend you leave your answers in fraction form. It'll help when it comes to reducing your radicals or reducing or rationalizing a denominator. Again, I'm solving for a because I need to know what a equals so I can plug it into the ratio portions of the other parts of the triangle. It says a equals 1/2, so the shorter length is going to equal 1/2 because it's half the length of the hypotenuse. And this one, when I plug in 1/2, I get 1/2 times radical 3. I can write that radical 3 as radical 3 over 1. I get radical 3 over 2. So these are our two lengths. The longer leg is radical 3 over 2. The shorter leg is 1/2. A pretty straightforward example with having a hypotenuse that has a length of 1. All right, that covers the notes. Now, what I'd like to do is I want to give you guys the assignment because I want you guys to work on that in class. So if you do have problems as I'm walking around, you can ask and I can help you out. Because I think you doing the practice is going to be more important than me standing up here delivering the notes the whole time. So if you guys can have your notes out. The one thing I would recommend that you have written down on a sheet of paper so you have access to it is this triangle, right? No, yeah. This triangle right here, where you've got a radical 3, and 2a. Okay, you've got those labeled and how they correspond to where the 30, 60, and 90 degree angles are.